Hey, hi everyone. Today's topic is document understanding and OCR using transformers. Okay, so now what we will do is the contents of today's session is we'll talk a little bit about PhonePe. Then we'll go through the problem statement. Then we will also see the practical limitations before jumping on to the models. Next, we will have overview of layout LM models. And then after that, we will also have hands-on Jupyter notebook where we will cover layout LM V2 and layout LM V3 benchmarking for the core data set. So about PhonePe. So PhonePe started in 2015, and when you look at the key milestones, so in 2016, it launched the Android app, which is built on a UPI interface, and then we also launched P2P bill pay and recharge. Then again in 2018, started the Bangalore data center and also launched the offline unorganized merchant segment, which is PhonePe for business. Then in 2021, PhonePe basically crossed 2 billion monthly transactions mark, and PhonePe now also digitizes 25 million kiranas across India. So also PhonePe becomes the first player to cross a billion transaction mark on UPI, and currently we have a market share of 46% in UPI. Where we are now is we have 415 million registered users. Then we also have 185 million monthly active users with 6.5 billion app opens and almost around 3.6 billion monthly transactions. We also now have 2,400 plus billers which are live on the app. So that basically explains the sheer volume of data as well as the market share currently which we have. And about the PhonePe vision is the PhonePe vision is to build a large, scalable and open transaction ecosystem that creates maximum positive impact for all stakeholders in the ecosystem. Great. So now coming to the problem statement. So the assumption currently I'm making is, everyone has little bit understanding of transformers and also understand about embeddings, and of course, the rest of the concepts, everything we will cover into the talk as much as possible. And of course, if I'm not able to cover the entire part, or if you have any questions on the concept, just feel free to connect me on LinkedIn and ask the questions. So now the problem statement is what we are trying to solve is given the particular image, which has, let's say, a text in it, and which also has some layout mentioned. So can we basically read, understand, and analyze all these business documents where, of course, we have some structure associated with it or some layout associated with it? So can we first extract text and classify? Or can we do the form understanding? Can we also do the document classification? Now, when I say extract text and classify, so essentially, if you look at these particular atoms, can I classify this particular text and a bounding box into some class? That is what we are trying to look for in this particular talk. What we are also trying to do is, understand the interaction between text and layout. So now given the text, which is the actual OCR extracted output, and the layout, which is basically the bounding boxes, can we also have, the visual embeddings attached to it, which are basically coming from image? And then can we take advantage of multimodal inputs, including, token embeddings, then layout embeddings, and also the image embeddings? So that is what we'll try to cover in this particular talk. Now, before again jumping to the actual implementation and the theory behind these layout LM models, we need to look at some of the practical limitations as well. So for example, data collection. So it could be like really time consuming, and it might have, some regulatory requirements as well. So when we look at the data which is available open source, let's say, for example, in this case, we are using the core data. So the data comes up with the annotations. Each bounding box is annotated with some label. So even so doing all those manual labeling and annotations, it does take a lot of time. So that is one practical limitation. Another thing is the image quality issues. So when we look at again the open source data, it is generally clean, and we don't encounter much of the bad images. While in the practice, we do come up with images which are basically might be cropped images. It might be, the rotated images at various angles. Someone might just click photos at different rotations. It might have various backgrounds, the blurriness in the photo, or even the poor light issues. So when we are actually trying to implement the models in practice, we do have to face all these challenges. And again, when we look at the production and deployment, the size of these models is pretty huge. So it might create some issues in the latencies as well. So these are the practical limitations, in fact, are in general associated with any machine learning solution which we are trying to design. But yeah, so in this case, the same applies. Another word is, are we using the sledgehammer to crack a nut? So for example, before jumping to the layout LM models, which basically involve the transformers and all those things, it's always better to look at the simpler methods first. So for example, in this case, suppose we need to extract a PAN number, which basically has a specific format, which is the first 5 letters are essentially these are the letters, then you have some digits. So it has very specific format. So now in this case, if our goal is to extract this permanent account number from PAN card photos, then probably we might not need, and of course that is the only thing which you need to extract, then probably you might not need the layout and all those things. You can essentially simply go for the available OCR models. And in fact, you can also use regexes to extract that specific format. So that basically says is, we don't have to always go complex. So if the solution actually demands using complex method, then only we should go and go ahead and start working on those methods. One good thing about trying out simpler methods first. And
Rohit, sorry to interrupt you, but some of the participants are saying that to be a bit slow, they cannot get you. Can you
okay,
please?
sure, no worries, no worries. So what we are saying is we should be able to try simpler methods first. And when we try the simpler methods and start benchmarking against them, then we are also able to justify why particular complex method is needed. So that is again, one benefit. And of course, so if someone has missed what I was just talking about is whenever the simpler methods are available, go ahead and try those methods than, immediately jumping onto the complex methods. So now for this particular talk, what I've selected is 3 models, those from the layout LM models, which is basically layout language modeling models, which are layout LM, layout LM v2, and layout LM v3. There are some other models like Donut, which I have currently excluded, but of course, feel free to go ahead and try those out on yourself. So for the time being, we will just limit to these 3 methods. So now, for example, when we are so before going to the comparison summary between these 3 models, what we can say is, it generally uses these 3 type of features or embeddings. Then one is the text. So whatever OCR model is able to extract as text, so that goes under the text, which is basically, for example, in this case, we could see this 1001 choco bun or something. Then the second thing is about the layout information, which currently we have with, let's say, the bounding boxes, the 4 coordinates of the bounding boxes. That also gets used. And when we are talking about the image features, those features we can get through, the CNN or vision transformer. Those might be specific to that particular image, and also the bounding boxes. So in any layout LM model, we will use the information, which is this multimodal and available as text, layout, and image. Now for quick summary of the models and the comparison between them. So the first model developed was the layout LM model. And the points which are there in this particular slide are from the papers itself. So what layout LM basically says is the pre-training of text and layout is separate. The visual features are then later combined to the text and layout information in the final fine-tuning stage. And the layout LM model, which is BERT plus, so it is essentially BERT plus bounding box 2D position as layout, and then you add the visual features through CNN, and then it becomes a one single model. So that was essentially the idea of the layout LM, to combine the model like BERT with the visual model with the visual features. Now, what happened in layout LM v2 is the pre-training now also included the visual part as well, along with the text and layout information. So that was basically was not there in the layout LM. So they added the visual features at the end, which is at the fine tuning level. Now in the layout LM v2, the pre-training consists of the images as well. Of course, it again uses the CNN features. Then it also used the text image alignment strategy and text image matching strategy. And of course, the details of all these terms and terminologies you can actually find in the paper, and those have been explained really well in the paper as well. So basically it is now a one single framework which has this cross-modal interaction. Another thing which paper also proposed is the spatial aware self-attention mechanism. And of course, the masking of text and a part of the image now is a part of layout element. After around 6 months, the layout LM v3 got proposed, which said that let's get away with the CNN features, and then let's use the structure which is very similar to the vision transformer, which basically says is directly leverage the raw image patches from the document images. Now it doesn't depend on the CNN. Again, the word patch alignment objective was used. Then it was again the unified discrete token, which used objective like masked language modeling and masked image modeling. And what it also proposed is it is a now general purpose model for both text centric as well as some image centric, which is the document classification tasks. I highly recommend to go through each of those papers, and in fact, they have also mentioned a really good structure, or basically the models, how they work. And now essentially we'll go to the notebook for the hands-on implementation. Any questions till this point? So let me just quickly check the Q&A. Will you be sharing data set here? Data set is called, which is available free. It is open source data. Will you share the notebook with us? Yes, I should be able to share. So essentially, when I say documents, it is better that we use the structured document which is available, and which OCR models were used to get OCR data from the images. We'll cover it in the notebook itself. The actual paper, it uses Tesseract as OCR engine, and we'll also show you in the notebook that what all other models we can use. Yeah, and the remaining we'll try to answer afterward. So now in this notebook, essentially what we are trying to do is we are going to fine tune different versions of layout LM models. And what we are trying to do is we are using the CORD dataset, which has the scanned images of the receipts. And it also comes up with the annotations, which are the OCR text extracted, then the bounding box associated with it, and also the labels for each of those bounding box. And yeah, so now the steps in this particular notebook is we'll understand the CORD data, we'll analyze the data, we'll see how the data looks, we'll get feel of the data. Then we will also understand the OCR. And for that, for this particular notebook, I have used Easy OCR, but of course, you feel free to use any other OCR engine which you have, which gives you the extracted text and the bounding boxes associated with it. The pre-processing of the data, so that we will do, then we will build 3 models, which is layout LM v2, layout LM v3, and we'll also try to benchmark these results with each other. And of course, the notebook is inspired from the work of this Niels Rogg. So feel free to again refer that. So I have made multiple modifications in that notebook. But of course, the credit to mention goes to the repo. And the key packages which are installed. I'm using currently Python 3.9. Use the transformers package, then Pillow, Easy OCR, and CV2 as well. So I've created this particular environment is called as transformers, and I've installed all these packages already. So now to begin with importing all the packages, the base packages are in general typical, which are in fact the OS, then random, the JSON we will need. So all the annotations are there in the JSON format. We will save our data in the pickle format. For visualizing the images, we'll use PIL, which is Pillow. Then for this particular models, we are using Torch, and the Torch vision is also required. Then from the layout LM, for the layout LM models, in fact, all the three, we will use the preprocessor and also the pre-trained layout LM models. And OCR, currently I'm using Easy OCR. We'll just go through one example, but we will not be doing much of the OCR as the data is already annotated. For someone who was asking about the data, so the data is freely available. This code data, you can refer to this particular GitHub repo, and you should be able to download the data. The data essentially consists of two folders. So it has three folders. In fact, it is train, dev, and test. And inside each of these folders, you will find again two folders, which is images and JSON. So images are again, this contain all the images, and JSON contains the annotations and the OCR output. Now, what we'll try to do is we'll run the paths first. And the first thing we'll try to do is visualize those images and annotations. So we'll just pick one image and we'll see how it looks. So the total number of images which are available in the folders are, in fact, we have for train, dev, and test, we have 745, 94, 93. And again, the annotations, now the number is slightly different. So not all the annotations match with images. Have taken care of this thing when I wrote the code as well. So now, for example, if I try to open this particular image, which is the receipt 0024, you could see it's the same image. I've used it in the presentation. And what it has is it has some structure which basically says some items which are purchased. It has some price associated with it. Then it also has the quantities. It has the total items, then total. Then in some of the images, you will also have the change price and all. So essentially, it has some structure of the receipt. And we'll try to see whether we are able to classify all the text output here. For the annotations, so the annotations consist of words and numbers extracted from OCR engine, the corresponding bounding boxes of it, and the labels which are associated with each of the extracted text. So let's check for the same image how the annotation looks. So we'll be using the valid line. And as you can see, for each of the words, for example, text total, we have all these bounding boxes associated with it, and it also contains the labels. Now, what we'll try to do is what all labels are there total, and this information you can get from the GitHub repo as well. We'll also try to draw the image and try to see how they have labeled. So the total categories which are there are menu, count, discount price, etc, item subtotal, etc. What we'll also try to do later in the stages, we will try to use fewer of these labels for the simplicity, but of course, again, it is not needed. You can use all the labels which are available, and again, it depends on problem to problem. Now, when I try to draw the image, you could see that each of the OCR output is tagged with that particular label. So for example, this particular item is tagged with menu and .nm. Then this one is also is a part of menu.nm. Then some of the outputs are, this is menu.count. This is menu.price. Then again, some of the other annotations are this total, then total credit card price and all. And as I was saying earlier, so getting to this particular stage itself might take time, because getting the data, then running the OCR, then manually tagging all these fields is a time-consuming process. So now for that, what we will try to use is OCR. So the bounding boxes in the receipt has been annotated, and let's assume that currently we don't have that particular data handy. So in that case, you can use your own OCR. And once the bounding boxes are ready, we can use any annotation tool of your choice, which has the OCR annotation facility, and you can actually get all those JSONs for you. So let's try to see one example for the same image. So I'm running the Easy OCR. So for that, I have installed two packages, which is Easy OCR and a CV2, which is not a contrib version. What it in fact gives, now if I run the results, if I loop through the results, what it will also try to do is it will give me the text, the probability associated with that text classification, and the corresponding bounding boxes. And when we try to visualize all the output, this is how it can look. So once you run, so suppose you don't have any, you don't have annotated data. So this is what you can do. Use Easy OCR or any OCR engine of your choice. Get the bounding boxes, get the text, go to the annotation tool, feed this data, and then manually go and maybe select each of the bounding boxes and tag them to a particular label or category. Cool. So now let's assume that we have all this data ready. What we are then trying to do is let's now prepare the data set. So for this particular exercise, uh, we'll write the functions to parse all these JSON files, and we'll prepare the data, which can be later fed to the models. Now for so what we have done is we are using same test train and val data, and we'll feed the same data to all the three models for benchmarking. We'll write this generate annotations function, which essentially reads the JSON file and creates list, which has extracted words, bounding boxes. Then we also have the normalized bounding boxes, which are later required for layout LMV2. We'll have the list of labels and of course the image names, so that we keep track of which image or all this list belongs to which image. And later when we are using the batch mode to load the data, we will have these image names handy. So we'll refer all these image names. So I have used the sample data from training test and val just for the simplicity purpose, and we don't spend much time in this particular session to train. Now, some of the functions, what we are saying is the normalized box, where we take the bounding box coordinate and we multiply it with 1000. So that is what is needed for actually feeding it to the layout LM models. The generate annotation function, what we will do is we will read each of the JSON file. Then we will extract, we have the image name. So we'll create the list of image names. We'll also create the list of words boxes, then the boxes which are not normalized, and also the labels. So let's run this and we'll also see, the output. Right. So I've run this for train, val, and test. Now, if we just have to look at the lanes and also the words train, which is this particular list, which contains all the extracted words. So this is how it will look. So this is for the first image. Similarly, what you can see is the list for the second image. We also have the labels which are used and which are associated with each of these extracted text. So that can also be, we can check. So these labels are also there. Now, as I said, the actual data will look lesser than 300. This is because some of the annotations are missing in the downloaded data. So that is why we have this lesser amount of data available here. Now, the next step is let's check the count of each of the label, and let's see, whether we want to use all the labels. So for today's session, decided to remove some of the labels, but again, depending on problem, as I mentioned, feel free to decide which ones to remove, which ones to use. So now if I just get the list of all the labels which are there in the data, and if I just want to check the count of those things, what I've tried to do is I'm removing the top this 10 labels which has lowest count, and we'll try to replace it with O, which basically says that it is outside the label. So model will try to ignore this O label. Rest of the labels we have enough data and can be considered. So now once we replace all data, let's again go ahead and check the count of each of those. So I think we have a respectable number of class representation. And of course, because we have used lesser amount of data, we might have lesser amount of some of the classes. So once we go ahead and use the entire data available, this won't be the case. Once we have all the labels which are in place, what we will do is we will dump all the train, test, and val data into pickle files. And that is where we can now look at the modeling stage. So now again for the modeling, we have all these pickle files which are dumped here, and we'll now start, we'll read them. And what we'll try to do is now we have to create indices of the labels. So the indices of the labels will be used inside the model, and the ID to label, which again converts back to the label, will be used for the analysis purpose, or when we are looking for the evaluation of the model or the actual prediction. So for that, the labels is the unique values of all the labels which are available in our data. When we write this single line, which basically says that for each label, assign the ID, and for each of those ID, get back the label. So which is label to ID and ID to label. So we'll run this as well. Once we have this particular label to ID and ID to label, so there is this function which will be used later, which basically compares, or which will spit out the classification report for the predictions and the actual labels. So we just run that. So there is this another function which is resize the corresponding bounding boxes. What it will try to do is in the layout LM models, we might have to resize the image to, let's say, 224 by 224 by 3. So for that, we will also have to resize the bounding boxes. And so this function will do that particular job. So it will resize and align all those bounding boxes according to the resizing of the image. So we'll also run this particular function. Right. So now, once we have these things ready, we will come to the layout LM model. So in the layout LM model, so again, just to recap, what it has is the pre-training of the text and layout, which is separate from visual features. The visual features, they get added in the later stage. The layout LM model is then becomes the word plus layouts, and on top of it, the visual features. So this particular step is kind of common for all the models. So we will write a class which is called as cord dataset layout LM class. The other class will be V2, another class will be there for V3. Each of those classes will read the data and will be later used for the data loader and batch operations. So what this particular class or the function, what it will do is it will read the image, it will resize the image, it will read all the words, labels, and bounding boxes, and it will tokenize them, which is again the requirement of the layout LM model. We will truncate the sequence, and we'll also read image and resize it as PyTorch tensors. So this particular class, if I just have to explain, we will take the words, then labels, boxes, everything from the annotations which we have created. We will mention the tokenizer, which is the bird tokenizer for layout. And for each of these things, we will have the list. So the step one is we take the index and read the image. So that is why we saved the file names earlier. Then for that particular image, we resized it. Then we also have the words, bounding boxes, and labels. So we for that particular image, we have these words, word labels, normalized and unnormalized word boxes. And then we take those and we transform it to a token level. So which is which will be later, we'll have the input IDs, attention masks, then token type IDs. If again, we are using, let's say, the question answer data, in this case, it will be all 0. We have the bounding boxes labels. So essentially, once the tokenization is done, we have the truncation of the token boxes, and whatever padding, etc., we are trying to do. For that, or in fact, for the tokens like CLS and separators, we will have the bounding boxes, which are this 000, and 1000. The encoding, which basically is the tokenizer output. So, and once this all is done, we will also read the image. Now for reading the image, what we are reading is we will read the resized image. We'll also read the resized bounding boxes. So that is why we wrote that function earlier. And we'll put all this. So we'll convert each and everything to the PyTorch tensors. So the output of this particular class, we will definitely visualize. So first, let me load the tokenizer, which is a pretend BERT base. So it might take a little bit of time. So till the time it loads, yeah, done. So now we have this train pickle, then val and test. We will use this class with the image directory we have given to read all those images. Tokenizer we have given. We have also given the base path. And now we'll try to get all these three data sets. Now, when we want to visualize how the data set looks, so let's try to see the first image in the train data set. So the input IDs, it is the tokenized output. So it has all the tokenization IDs, and the remaining whatever you can see as zeros, it is because of the max length, which we have given it as 512. Then the next we have is token type IDs. So currently we won't use that because this is the classification task of all those labels. Then for each of those IDs, we also have the attention mask. We also have the bounding boxes, which we have given. And again, for each of those words, we will also have the labels which are associated. And this is where we are using that label to ID and ID to label data. And of course, whatever is not there, we have just given the -100. We also have the resized image. So now this is for one single image. What we'll try to do is now we will give the batch size as 4, and we will use this data loader, and we'll pass this train data set which we have computed earlier. Now, if I have to look at the batch, how it looks and the sizes it has. So the input IDs is has the size of 4, 512. 512 is the maximum length which we have given, and 4 is the batch size. So each batch will consist of 4 images, and whatever is the other inputs which are associated with it, which is, let's say, word tokens and bounding boxes and everything. The attention mask and token ID types will have the same dimension. The bounding box, it is batch size. Then we have vital max length and 4 coordinates of the bounding box. Labels, it is again batch size into 512 for each of the image. So in a way, what we are trying to do is we are trying to convert each and everything to a sequence. Then we also have the resized image, which is essentially batch size into the image size, which is 3, 224, 224. Same goes with the other bounding boxes, which are resized bounding boxes and non-normalized. So all in all, the encoding consists of all these keys: input IDs, token type IDs, and what all we have seen here. If you also have to check the decoded output of all these encoded input IDs, this is how the decode will also look. So again, sometimes it is better to have a look at the decoded output first before we pass it to model for debugging purpose. If we have done something wrong, then we should be able to catch it here in this particular decoding. Again, what we'll try to do is we will see. So because we have resized all those images, so just to check whether, the bounding boxes also got resized and realigned, we'll also try to read the resized image from these encodings. So now the image is much smaller, which is 3, 224, 224. We will load the resized bounding boxes. So all in all, it looks okay. And so it's better to do this for the debugging purpose. Now we come to the actual modeling stage, and that is what we were saying earlier, that first we will try to get the pre-training of the text and layout. And later on top of it, once that pre-training is done, on top of it, we'll try to add the image features. So now this particular class, which is layout LM token classification class, this is what we are trying to do. First, we will load the model, which is the pre-trained model. It also needs the number of labels as one of the input. And once we have that, we will also use the ResNet model for visual features. And we also have this ROI align and projections, where what we'll try to do is we will try to use the bounding boxes images. We'll try to project it linearly so that when we combine it into the final layer, we will match all the dimensions of whatever output we are getting from the sequence, which is layout, and with the similar dimensions, we will have the projected features from the ResNet model as well. Now, once we go to the forward, we will have the sequence output, which is the output of the layout LM. So the dimension of this particular output is now batch size into 512, which is our max length, sequence length, and 768, which is of course the hidden features. And for the ResNet, this particular block of the code, it will try to use the feature maps and ROI align. So feature maps we have got for the resized image. The ROI align function, which we are using for each of the bounding boxes, we'll try to project it. And once we have done that, the projections, we will have the final output, which is basically the batch size into sequence length into hidden size. Now, when we say that, the pre-training happens separately, we have not used the visual model anywhere in the layout LM till this point. But here in this step where we are using both the outputs together, so this is the step where it will use the sequence output as image feature output. So it will add all these features. And once we have this as the final layer, we define the loss, which is our regular cross entropy loss. And that is how we have built the model. So we'll just run this. So now if you see, this is the final stage where we have combined these two output, and the visual features were not part of the layout LM or the layout model earlier, or text and the layout together. So now this becomes my model, where it will load the pre-trained model. And before, I think it will take time to load this. What we'll try to also see is now we'll actually go ahead and train the model. So now in this particular case, I have just used the training epochs as one, so that we save the time, and we don't spend time in training. But only for this particular case, we will try to run the model. So it's the same thing. So now with the use of train data loader, we have we get the batches. So we have these input IDs we get from batch. Then we have this bounding box, attention mask, token, label, resized and aligned bounding boxes. And we get this from output we call the loss. And once we start running it, yeah, I think it will take some time. So at this stage, what we can try to do, and we can go back and look at the architecture of the model. So now this is the architecture of the layout LM model. So this is what exactly we have done. So we have this position embeddings. We had this text embeddings. So position embeddings were basically the bounding boxes, and the text embeddings were the words extracted from the OCR output. So this is the part of the pre-trained layout LM model. And what we are also saying is, let's say we have this some document here. We have used some OCR or PDF parser. We get all these details. Now from the same image, we applied this faster CNN model. And whatever FC layer. So if you look at this final thing, which is the layout LM embeddings, which came from the sequence data, we just added the image embeddings. And whatever downstream task, in this case, we had the 17 class classification. So we only combined it into the fully connected layer. And now if I go back to the layout LM V2 model, here we should be able to see the difference where the image or the masking of the image is now also part of the pre-training itself. So that is the key difference. So one of the key difference between LM and layout LM V2. So rather than using the features separately, it becomes the part of the pre-training itself. And that is how we create layout LM V2. And of course, as I mentioned, there are other specific details in the paper, which make it a little bit different from the layout LM. And again, to compare the layout LM v3, they have gotten rid of the CNN. So layout LM v2 also uses CNN. Now they have gotten rid of the CNN, and they also use this multimodal transformers where you use the patches of the images for the embedding itself. And you use this mask language modeling head, the masked image masking heads. So with these two, we basically get the final loss. Yeah, so let it run. So I think I have the results ready below as well. So now when we come to the evaluation part, once our model is ready, we can now use our test data loader. So the test data loader, what it will try to do is the similar way we are using train data loader. We will use all the information which is available. We will get the output. And now the predictions are essentially the outputs.logits. And once we again have that, we will have the predictions, which are the labels it has produced, and along with it we also have the labels, and we should be able to check the result. So this was slightly different, where we didn't quite use the preprocessor part, which is given by the Hugging Face transformers. But in next layout LM v2 and layout LM v3, we will directly go ahead and use the preprocessor. So above, it was necessary to use different code just to show how internally it combines these two outputs. But for the v2 and v3, we will not do that. We will directly go ahead and use the preprocessor. Yeah, so let it run. We will come back to this. So now what this preprocessor will do is it will combine the feature extractor and tokenizer into one single processor. And it first uses feature extractor to resize document images to a fixed size. And here we can optionally apply the OCR as well. So now in none of these examples, we are applying OCR. So, but you have option to use OCR, but internally again, it will have the tesseract, which is getting used as OCR. So it will then get the words and normalized bounding boxes, so which is now common. Then once we have this layout LM tokenizer and tokenizer fast, it turns words and bounding boxes into token level input IDs, attention masks, then token type IDs and bounding boxes. So optionally, again, we can provide integer word labels, but here we will see that we'll just give this label to ID everywhere. So this is at 61%. Okay. So the preprocessor, we will read the layout LMV2, and just like the way we wrote a class for layout LM, we will start writing class for layout LM v2 as well. So now in this case, again, we are using the same data. So for example, if I just go down, so we are again using the same train, val, and test data. I'm getting those annotations here. Then using the batch indexes we have, I'm getting the words list, the bounding boxes list, and the labels list as well. Then I converted all those word labels into using label to ID, and I pass it to the encoded inputs. I basically want to now get the encoded inputs, which is the output of the processor which we have used. Of course, the input to that is the image array. Then we have the words list, boxes list, word labels list. Padding is max length, which we are saying, which is 512. Truncation, we are keeping it as true. And the return tensors, we want the PyTorch tensors. Once we have all this encoded output ready, we will also write some of the assert statement just to check the sizes matches. And exactly the same way what we did for layout LM, we will get the train data set. We will also get the data loader for batches. Now, just for the example sake, I have taken the batch size as 8, and feel free to refer to the paper where for the configurations they have used to fine tune it to the chord data. Now, in this case, again, the difference is we only have these keys of the encoding is input IDs. token type IDs, we have the attention masks, then we have bounding box, we have labels, we have images. And just the way we had looked at the train data set here also, it is exactly same. It's just that now we are not dealing with non-normalized boxes. So all that thing will get taken care inside the modeling stage. The sizes, again, those are the same sizes for the training data. Again, if you want to have a look at the decoded output of this particular thing, we should be able to visualize it. And it is always better to have this decoded output once checked. Also, now if you want to have a look at how the model or how the preprocessor is assigning all these labels inside. So it will begin with CLS, it will assign -100 as label. Then the total is, if you again convert this 4 to label to ID, you will get the label associated with. So each word, each of that extracted output will have some label associated with it. Cool. So I think what we also have is the layout LM has done training. We can just go ahead and run the predictions. And this should be done fairly quickly. Let's just wait for this thing to run. It is done. So for the first epoch which I've used, I'm getting the F1 score of around 0.78. So similarly, again, what we have is for this layout LM v2 and layout LM v3, it's exactly same steps, exactly same data. It's just that the input changes a little bit, and the internal working of all these models is definitely they're very different from each other. So we looked at the layout LM v2, then same goes for layout LM v3 as well. We have written the class, and then if I run particular exercise, what we have is again the results. Of course, we should not be comparing these particular results for benchmarking, because again, we have just run one batch of it. Now, if I have to look at the, in the backend, I ran different experiments with higher epochs. Then there I'm able to get the difference in, so in fact, as mentioned in all these papers, the benchmarking, it really works. So I'm getting high F1 score for layout LM v3. Then the second is the layout LM v2, and the third is the layout LM model. So once you start increasing the epochs and you start using more and more data, you will get better accuracy. And now when you want to put it into the actual practice. So for example, now I don't have any image. I don't have any annotations ready. I just have the image. Then the way I do it is I apply the processor on that image. I get the list of all those words. So first I apply OCR. I get the extracted words. And then once we have the words, we will not have labels. We will have the bounding boxes. I will use the processor part. And when I try to predict it, so I will get the classes for each of those bounding box. So for example, I've done it for one single image here. So this is what you should be able to get at the end. So given the text and bounding box, you will have some class which this layout LM model has predicted. And then you can use that class and whatever information is actually needed for you to go ahead and maybe do some automation, you can go ahead and do that. So for example, in this case, I might have to get all the items which are there. So I should be able to do that, or whatever. If I have to do some sum or something, I should be able to do that on this extracted output and the classes. Cool. So I think this is it. I don't know if we have time to look at the questions, or in fact, we are already exceeded the time. So what we can do is just feel free to ping the questions on LinkedIn, and I should be able to answer that there. So I think we already exceeded the time.